Alright, in this video we've already talked a little bit about complex numbers, but we want to know, or hopefully if you're watching this, you want to know what the complex plane is all about. Also how to do one more number operation, the absolute value of a complex number, as well as deal with powers of complex numbers, or at least powers of I, in order to help you deal with powers of complex numbers. So first of all, we have to understand what the complex plane is to help us with both of those other thoughts, absolute values and powers. The complex plane is basically saying that you have sort of a two-variable plane going on. You're going to deal with real numbers and imaginary numbers. Because remember that complex numbers are made up of a real part and an imaginary part. So if you want to plot those, it's kind of like plotting on a number line. The real axis, what used to be x-axis, but now the real number axis, is essentially just a very large number line. It's just traveling left and right. So 0 is at the origin, and all we want to do is go out to the number 4. So we're just going to the real number, 1, 2, 3, 4 units out to the right. So if we plot that point, that is K. So we can label that point. Now, if we want to plot the point negative 2i on the other hand, remember imaginary numbers are not real, so they can't happen on a real number line. So we can't go left and right, we have to go a different direction, which is where the imaginary axis comes from. What used to be the y-axis is now the imaginary axis I. So we're going to go exactly 2 units downwards. And this point at negative 2i, remember we could label M, because that's the point, negative 2 units from the origin, downwards on the imaginary axis. We didn't go left or right at all, so there's no real portion. We just went directly down to negative 2. Which means if we want to plot the point T, we need to travel in both directions. I need to go negative 2 units on the real axis, but I also need to travel 5 units, 1, 2, 3, 4, 5, on the imaginary axis. So both going left 2 units in the real portion and up 5 units in the imaginary, this would be the point T, negative 2 plus 5i. Now that complex plane will help us understand how to find absolute values of complex numbers. If we think about where the graph of negative 2i would be on our imaginary and real complex axis, we went directly 2 units downwards. So remember the absolute value being the distance from 0, absolute value equaling distance from 0. Well, we went exactly 2 units down to negative 2i, or negative 2 on that imaginary axis. So therefore, we are exactly 2 units from 0. The same thing works for a more complex, rather than a pure imaginary, a complex imaginary number. So if we imagine our graph here, we're going to go 1, 2, 3 units to the right and 1, 2, 3, 4 units up, basically putting us at 3 plus 4i. Well, the distance from 0 then is actually a diagonal line. But that diagonal line also forms a nice right triangle. 3 units at the base and 4 units on the side. And if we remember a simple Pythagorean theorem, 3 squared plus 4 squared equals c squared. Therefore, 9 plus 16 is 25. And if we take the square root, c will equal 5. Square root of 25. Therefore, the distance from 0, the distance from our origin, is exactly 5 units. Go ahead and try that same idea given the 2 complex imaginary numbers here. Use a graph, imagine your diagonal, and see if you can't find the hypotenuse of the right triangle giving you the distance from 0 for each of these complex numbers. Pause the video now. Alright, on the top, you had negative 2 going to the left, 3 units going up. So negative 2 squared is 4, 3 squared is 9, and you get 13. But remember, that's equal to c squared, so don't forget, your final answer would be the square root of 13 units. On the bottom, we've got 5 minus 5i, so we went right 5, down 5. Again, 5 squared plus negative 5 squared being 50. But again, that's also equal to c squared, so take the square root of 50. Breaking that down into a 5, and a 2. 5 being on the outside. So a nice, clean, exact, simplified answer would be 5 root 2. I hope that helps you with the absolute values of complex numbers. Now, one other thing we're going to discuss here is also powers of I, because technically in complex numbers there are only real portions without imaginaries, and complex portion or imaginary portions that only have an I to the first power. Any other I can always be broken down either into -1, 1. So let's put those on our graph down here. -1 and 1 in the real numbers, or I or -I in the imaginary numbers. And we'll show you how here, like this. I squared, we already know, hopefully you've looked at before, is really the square root of -1 squared. So square root squared breaks down to -1. Well, the beauty is any larger power can be broken down into i's and I squareds. So i's being I to the first, or I squareds being real numbers. So I cubed is really I times another I, but remember 2 of those at a time change into I squared. So you really have I times -1, or essentially -I. So this is really the same thing as I to the third. Well, I to the fourth is I squared times I squared, which would be -1 times -1, which comes out to 1. So again, this is the same thing as I to the fourth. And if we go back over here and label our I squared, notice that at the top of our graph we've got I, then we have I squared, I to the third, and I to the fourth traveling around our circle in a cycle. I to the fifth is really I times I to the fourth, so I times +1, or just I, which takes us back again to the beginning of our cycle, or to the first step if you want to look at it that way. I to the first and I to the fifth are the same thing. So then you could keep going around I to the sixth, I to the seventh, I to the eighth, and you get the idea. It just keeps repeating the pattern. Every fourth step brings you back to the beginning. Well, if you want to find something like I to the 35th, and there's a 4-step cycle, the first thing I would do is take 35 and divide it by 4, realizing that this comes out to 8.75, which means you're going to take 8 full trips around the circle, because that's 8 full cycles of 4, with an additional 3/4. This is 8 3/4, which means that 1 extra quarter would take you up to I, the first step along our cycle, second quarter over to I squared, or -1, and the third quarter down here to -I. So I would say that I to the 35th is really the same thing as -I, because all of the other i's would have canceled away. This is I to the 35th power. Let's do the same thing with 7,682. Notice it's already even, so I expect to get either -1 or 1 of those even powers of I. But if we take a good look at it, let's jump on our calculator real quick. 7682 divided by 4 is going to give us, and we better go ahead and press Control Enter to get our nice decimal. It's going to give us 1,920 and a half. 1,920 and 1/2. Well, that's 1,920 full cycles with an additional half a cycle, which again, if you're starting at 1, for any time 4 goes into 4 evenly, 4 goes into 8 evenly, that extra half is going to take us over here, leaving us with I squared, or essentially -1. An extra half a cycle puts us halfway around that circle. I hope that helps you with powers of I. If you have any further questions, make sure you check with your teacher. Good luck, and happy complex numbers.